So like I said, today we have a double feature, and our first speaker today is Mike Gadd. So Dr. Gadd is a research scientist at the Geological Survey of Canada and specializes in the geochemistry of sediment-hosted base metal deposits. His research applies bulk and microanalytical techniques to these mineral deposits to determine their geochemical evolution and to build genetic models. He is currently working on shale-hosted nickel, zinc, molybdenum, rhenium, PGE mineralization in the North Yukon. Dr. Gadd received his bachelor's from Tennessee Technological University and his master's and doctorate from Queen's University, where he is also an adjunct professor, co-supervising graduate theses related to the geochemistry of base metal deposits. Looking forward to hearing from you, Mike, so go ahead.
All right, well, thanks, Wren and Filipa, for this opportunity and invitation to speak today to the group. And so I will be talking about, it's a bit of a synthesis of the work that I've done on the genesis of hyper-enriched black shale, or HEBS, nickel, moly, zinc, PGE, mineralization in the northern Canadian Cordillera. And so before I get started, I've got a laundry list of people who I couldn't, it wouldn't have been possible to complete this work without. And so my colleagues and co-authors at the Geological Survey of Canada, at Queen's University, my colleagues and students, colleagues at Yukon Geological Survey, at University of Alberta, at the Calgary office, as well as financial support from the GSC through the Targeted Geoscience Initiative, and logistical support through the Federal Polar Continental Shelf Program. And so as we get into the talk, I think I will just describe briefly what hyper-enriched black shale deposits or polymetallic shale deposits are, and especially in the context of the northern Canadian Cordillera. And so there they are thin and geographically widespread polymetallic shales. In Yukon, the mineralization is very high grade with abundances of nickel up to 7 weight percent, molybdenum, thousands of ppm, zinc, weight percent, platinum, hundreds of ppb, same with palladium, high abundances of gold, iridium, ruthenium, extremely high abundances of rhenium and selenium, arsenic, just to name some, but they're hyper-enriched in other elements as well. The best examples in Canada, or the most mineralized example, like the highest grade mineralized examples in Canada, occur in Yukon and British Columbia in Devonian black shales. And so I've got the highlighted, or the areas that I worked on highlighted in the red ovals. And I'd say that there's probably significant potential for further discoveries, but the overall poor understanding of this style of mineralization hampers exploration. And so today the talk will focus pretty much exclusively on Yukon, but work on stuff that's happening in the BC hyper-enriched black shales is forthcoming, but it'll be mostly Yukon today. And so the purpose of the work then is in recognizing that that HEBs are important globally resources for base and precious metals, but also critical and strategic metals. So recognizing that and that they are mined in Finland and China and Poland, either historically or currently producing, that our lack of understanding in Canada really kind of puts us at a disadvantage. And so we have this style of mineralization, but it's poorly understood. And so so my goal and the goal of my colleagues is to really determine the lithological, geochemical, and temporal controls on mineralization, with the salient goal of developing an internally consistent genetic and exploration models that account for the geological features that and will ultimately aid people interested in exploring for these. And so I have here examples of genetic models from China that kind of underpin the work that we're doing, because some of the best analogs globally for what we see in Yukon are in China. And I won't go into a great amount of detail, but I'll say that there's a seafloor hydrothermal model that's akin to a sedimentary exhalite style hydrothermal mineral deposit. And then there's a seawater scavenging model that suggests that all the metals that form in these HEBs form from direct scavenging from seawater. And so they're not really compatible. And so, and exploring for these would require different strategies. And so understanding that, and then the kind of this theoretical underpinning is what's helping guide our research. And so in Yukon, there's 4 really good examples of HEBs that we studied, and all of them are hosted in Devonian black shales. And so in the Richardson Trough, which is in northern Yukon, the Devonian looks like this. So you have the Road River Group, Cannel Formation, and Imperial Formation. And the money shot is right at the Road River Group, Cannel Formation, regional stratigraphic contact. And so the HEBs are at this consistent and predictable stratigraphic position in all the northern Yukon localities. And so you can see that when we zoom into the 4 different localities here, they're just B, C, D, and E, but it's Moss, Peel River, Monster River, and Nick. The local stratigraphy is basically all the same. So there's carbonaceous siltstones and shales that are interbedded with or overlain by carbonate concretion-bearing black shales that then have barytic or calcite nodule-rich shales, on top of which is the hyper-enriched black shale mineralization. And then the Cannel Formation is pretty much uniformly turdy, silicious black shales. And so at one locality, Peel River here, you can see that there's actually several discrete layers of the sulfide mineralization. So we discovered this in 2017 when we were doing field work. And so this is rare, and we tried to find it at all the other localities that we visited, but have so far not had any luck. And so, I mean, one of the persistent questions that we haven't really answered yet is why this is the case. But it's a really intriguing development that we found, and it adds, I guess, adds to the intrigue of the nature of this style of mineralization in Yukon. If you're in the field, you basically look and see these pictures here, and there's not really a whole lot to look at, especially if you're standing back. So like I said before, they're thin, and so we're talking about centimeter scale thickness, but and fairly nondescript. And so but you can, once you hone your eyes in on what to look for, it's pretty easy to find. So if you're in the right neighborhood and in the Devonian shales, you can pretty much consistently see very large carbonate concretions interbedded with black shale, usually because of the weathering. There's a rusty patina on the concretions or on the shales, and transitions into a pretty nondescript layer of mineralization. And just to get an idea, the concretions are meter scale or bigger. So that's a person right there for scale next to a carbonate concretion. When you zoom in, you might see some interesting features in the HEBs. And so here's just an example of plant remains, woody plant remains that have been totally replaced by sulfide mineralization. And I'll get into that in the next slide. But you might also see on a fresh surface laminated to semi-massive sulfides that are interbedded with black shales, or even just totally nondescript black gungy recessive weathering shales. And so in the field, like I said, you can identify this if you see carbonate concretions and that are underlain by more resistant cherty black shale. That's a pretty good sign. So one of the really cool features that we found when we were in the field is actually preserved in bedding plains woody plant fossils. And so it's interesting and important for a couple of reasons. And so at Peel River, we had the most photogenic opportunities to see and photograph these. And so this is just looking down at a bedding plane, and you can actually see really well-developed branches, and these branches are entirely replaced by sulfides. This particular example wouldn't have traveled very well, so we just took pictures of it. But I was able to get a better and more resistant sample back to the lab and cut it. And you can see in these cuts here that you have primary plant or tree branch phylum that's entirely replaced by sulfides in both cross and a long section. And so these branches have what we interpret to be a pretty uncompacted or original aspect ratios. And so that means that they were replaced by sulfides long before they were deeply buried and could compact, because they, they basically look like they would have the same aspect ratios as they would when they were, on the surface. The fact that they're entirely replaced by sulfides indicates that whatever reactions were going on in the sediments, it was able to basically replace far less labile organic material. So terrestrial plant remains are a lot less susceptible to bacterial sulfate reduction than marine organic matter, but all of the terrestrial organic matter was replaced. And we know that bacteria play an important role based on sulfur isotope compositions of these sulfides, which are uniformly negative. And so this is cool, but also important in terms of understanding the formation of these deposits. And so here's just an example of one of the localities, the moss showing, and it's bulk lithogeochemistry and proxies, and some of the trace elements as well. What makes the hyper-enriched black shale exactly that. And so you can see from silica and terrigenous input that you have pretty normal shale sedimentation up to the hebs, where the clastic supply is effectively cut off. And then into the hebs, you have high abundances of iron, and then all of these trace precious and base metals. And then followed by, in the canal formation, which overlies the hebs, a very effective silica factory. And I don't have the plots, but it seems like, based on looking at different elemental trends, it's pretty much all biogenic silica in the canal formation, compared to in the rocks that underlie that's more clastic silica based on terrigenous detritus shed off the continental off the continent. And as I said, we have done some sulfur isotope work done some of the different hebs, and they show uniformly negative sulfur isotope compositions. And so this is a bulk sulfur isotope composition, but even looking at SIMS data, it's pretty much the same. And so then we can compare the different localities. So the one I showed you was Moss, but at Nick, Peel River, and Monster River, you see the regional stratigraphic content, extremely high abundances of all these metals. And so this is always the top of the Road River group, and underlying immediately the canal formation. And so in terms of the timing of mineralization, I've done quite a lot of petrography and laser ablation work, but I've just picked one photomicrograph to highlight really what I thought did a good example of showing what the relative timing of the mineralization. And so here we have bedded pyrite, which is sooty, and it's sooty because it's got a lot of silica or silicate bits in it, and carbonaceous material that's cross-cut by a pyrite marcasite barite vein. The vein obviously postdates the bedded sulfide mineralization. And so if we go and we look at a blown up area here on the right side, you can see where I did some laser ablation work. And the laser ablation work it's very convincingly shows that in the bedded sulfides, or in the bedded, it's mostly pyrite with maybe some trace nickel sulfides, that molybdenum, palladium, rhenium, platinum, gold, and a slew of other elements that aren't shown are in this bedded sulfide, whereas these later veins are effectively devoid of all of these, or most of the target metals. And so there's a little bit of nickel and maybe some other metals that are in these veins, but we know that based on these cross-cutting relationships and chemical compositions, that a significant portion of the metal load was deposited during diagenesis. These are typical diagenetic textures that have incorporated a vast majority of these metals. And so from a relative timing standpoint, we know that metal sequestration is early, and limited mobilization that is present didn't really remove any metals. And so we have the timing, but what about the age of mineralization? And so because of the really high rhenium, and because although it wasn't maybe clear in one of the past pictures, there were conodonts that were in the rocks. But at any rate, we were able to do rhenium, osmium geochronology, and conodont biostratigraphy to get a chronological framework for the hyper-enriched black shale mineralization. And so here's a snippet of the Devonian that's centered on the middle Devonian. And looking at Peel River, Nick, Moss for rhenium, osmium, and Monster River for conodont ages, they all pretty much stack into they're identical within error, but they're all like quite close to each other at any rate. And so what we can, and when we compare the conodont age to the rhenium osmium age, we can say with confidence that the age of sedimentation is pretty much the same age as mineralization, which suggests that that mineralization is synchronous with sedimentation. So it's synsedimentary, basically a synsedimentary deposit. And so, and it's like this across the tens of thousands of square kilometers that these deposits are, they're all at the same stratigraphic contact, and they're all across North Yukon. And so we have then to wonder about how the metals got there. And so I'll try to explain that in the next couple of slides. And so here I took an example from Monster River, but the rare, and I'm looking at the rare earth element yttrium systematics. And so these are just a few representative samples, but I draw your attention to particularly the cerium anomaly and this positive yttrium anomaly. And so the cerium anomaly is noteworthy because when you think about massive sulfides or sulfidic shales, you don't normally think of a negative cerium anomaly, which is indicative of oxygenated or at least semi-oxygenated water. And so that happens by scavenging of cerium by ferromanganese oxyhydroxide particulates. And those ferromanganese oxyhydroxides scavenge rare earths and basically, especially cerium, leaving seawater and what remains with seawater as is depleted in cerium. So you get this negative anomaly. The same happens with holmium relative to yttrium, and so these ferromanganese particulates scavenge more holmium than yttrium, and you get a positive yttrium anomaly. And so when we look at a cross plot of yttrium holmium versus cerium anomaly, you can see here in the Hebb samples that the highest yttrium holmium ratios, which are right smack in the seawater range, are the most negative cerium anomalies. So this suggests that at the time of the Hebb's formation that you have the most active particulate scavenging. And the other thing about ferromanganese oxyhydroxides is they scavenge a whole bunch of metals. And so I'll talk about that a bit more in this slide and the next one as well. And so here we have a plot of modern seawater abundances of metals versus hyper-enriched black shale abundances of metals. And so we have this linear trend at about 1 to 1 million that show that, and so this plot in the linear trend indicates that you have basically quantitative scavenging at a rate of 1 to 1 million compared to modern seawater of metals from seawater. And so if it was a shotgun blast pattern with elements all over the place, it wouldn't indicate metal scavenging from seawater, but because it's a nice linear trend, it strongly indicates that metals in the Hebbs are scavenged from seawater. And so if we also look at continental crust normalized plots of Hebbs from Yukon and also from China and compare those with modern seawater, you can see basically the exact same topology for all of those. And this has been used to argue for seawater scavenging of these metals. And I guess and I should probably say that one of the reasons that seawater scavenging is presented as a model is because there's really not anything preserved in the geological record that supports hydrothermal mineralization. So there's no alteration zones or large scale structures or really small scale structures that could be the conduits to transport metalliferous fluids. And so while it's may seem a little far-fetched, there's not really there's not good physical evidence for hydrothermal transport for these deposits. And so with that, I tried to develop a conceptual genetic model for how we think that the deposits formed. And so we know that based on different geochemical proxies that we have, redox stratification and metal scavenging and sequestration, which allowed for the formation and of ferromanganese oxyhydroxide particulates that scavenge metals. And so in this low stand seawater in the Richardson Trough, you have basically it's open marine. And then as seawater rose during the Middle Devonian, you can exchange, or there's an influx of seawater that's nutrient rich and it drowns the platform, cuts off clastic sedimentation, and possibly even washes, depending on where depending on where the trees are, could be promoting the transport of the terrestrial plant matter to the basin. But at any rate, you have the situation where there's a bunch of nutrients that are promoting the formation of ferromanganese oxyhydroxide particulates that scavenge metals. And here's just a schematic diagram of what those might look like. So you have manganese and iron oxyhydroxides that scavenge metals, and then they get deposited below the chemocline. The manganese dissolves, and then all the metals associated with that are dissolved as well, but the iron oxyhydroxide are a little bit more stable, and so they can be deposited on the seafloor, after which they are reduced and turned into sulfide minerals associated with organic matter remineralization. And so to wrap things up, the Middle Devonian and really most likely the Upper Eifelian to Lower Gavidian is the age of mineralization in Yukon. When considering exploration, really if you can put your fingers on the Canal Formation Road River contact, that's going to be your highest likelihood of success. But keeping in mind that the mineralization is dark and recessively weathers. So if you can't see it, maybe you'll see the carbonate concretions. And so our model that we favor is the ambient paleo environment in which highly efficient scavenging of metals and metalloids from seawater is operated in tandem with low rates of clastic sedimentation. So there's no dilution with clastic detritus and really efficient sulfide mineralization. So with that, I thank you all for your attention.
Thank you, Mike. And so while people are still gathering their thoughts, I'd actually like to ask a question to you, Mike. I might have missed this, but you mentioned that in some of the fossils, the uncompacted nature of the plant, or the fossils, I wanted to ask, what is the relationship of its compaction with the age of replacement?
So if it was a late replacement, like after deep burial, then you would expect the plants to be smushed. And so the fact that they aren't smushed, I've interpreted that to mean that it happens pretty close to where basically near the sediment water interface during early diagenesis. And there's quite a bit of research that says also that in the right environments, plant replacement, the organic carbonaceous tissues start to be replaced pretty quickly after they're deposited. And so it just means that the rapid replacement would allow it to be a bit more resistant to compaction.
Okay, all right. So it's kind of the more smush, the more likely it's older in terms of the replacement.
The replacement happens deeper after deeper burial.
Oh, okay, I get it. All right, yeah, thanks. All right, okay. Filipa, do you have a question?
Yeah, we have a couple of questions. So Gideon, you want to unmute yourself and ask the question?
Okay.
Thank you.
All right. Hi, Mike. I'm just wondering if you can, according to what you have explained, if this can be used to explore for vanadium deposits in sedimentary, in black shales around the world.
I mean, yeah, I don't see a reason why it couldn't be used but I don't see why it couldn't be used or something similar, although I don't I think that usually with vanadium, there's more of a hydrocarbon component. Like I know that in Yukon, there's vanadium-rich black shales, and that's usually associated more with a hydrocarbon component. But we don't see that. Actually, it's interesting because these particular thin sulfide-rich mineralization don't have much vanadium in them, but the enclosing rocks do. And so I don't see why it couldn't be, but they don't exactly conform to this example in the Yukon. I don't know if that answers your question or not.
Yeah, no, it answers my question because I was just wondering from the figures you showed, vanadium was not that enriched, but the explanation was kind of, yeah, scavenging the metals from the seawater. Sound like a good model to target vanadium deposit, but my worry was, why is there not that much vanadium enrichment in those black shales as compared to the surrounding host unit?
So that I don't have a great answer for that question. I could guess, or I mean, I have some ideas, but not a definitive answer. I think that most of what's left of the organic matter in the Hebs samples itself is it's basically the dregs. Like there's not much left, and so and generally the vanadium is associated with the organic matter in these rocks, and so there is relatively high TOC, but it's very over mature, and so maybe the vanadil compounds would have been like cooked out or something and remobilized elsewhere.
Thank you. Thank you.
Thanks, Gideon, for your question. Our next question is from Anne West Hughes, and she'd like to ask, are the carbonate concretions a general feature of Hebs or locally/regionally important in the Yukon? In other words, are they important for the formation?
Well, there's lots of carbonate concretions throughout actually the Road River group and Ern group / Cannel formation in Yukon, but we think that the localized and really large concretions, that's a question we're still trying to answer actually, but we think that they are important because the reactions that cause the biogeochemistry of carbonate concretions ties in closely with production of reduced sulfur, and it could be important, for example, to create, that might be one of the key reactions in the forming those concretions, maybe one of the key reactions in creating the reduced sulfur that ultimately traps the metals. And so some of the work that I've been trying to do, but has so far been unsuccessful, is looking at the organic geochemistry of the concretions and the host shales to see if there's a way to fingerprint the types of organisms that would have made the right conditions and made the actual reductants that would have trapped the metals, but we don't have a definitive answer for that yet. But it's curious that there are lots of carbonate concretions all throughout the Road River group, but it seems like the Hebs are concentrated in this one pretty narrow snapshot.
Okay, thank you very much. We have another question. Let me see. From Dennis Ashoki. Do you want to unmute?
No? Yes, I can.
Okay, thank you.
So my question was more of general, maybe to everybody. So my question was, if we have a hydrothermal action underwater, how will this compare to hydrothermal action on under continental areas? And I ask this because you mentioned somewhere that you have not been able to see any hydrothermal alteration halos below the Hebs. So I was wondering, how will hydrothermal action, how will the alteration halos of hydrothermal action underwater compare to alteration halos for hydrothermal action in continental areas?
So I think that I guess the question about hydrothermal and like how important hydrothermal activity is because we have effectively mineralization that's all the same age or about the same age at the exact same stratigraphic contact, but there's not really there's not really any indication of a way to transport a hydrothermal fluid to all of those places at about the same time. And so even if it's in sedimentary or early diagenetic, we still have to somehow get those hot metalliferous fluids to a very, very large area at about the same time. And so that's where, and there's not any large structures and or anything that would be supportive of large scale, like, you know, at the Richardson Trough scale, fluid event at this time. Like we just don't see anything like that.
Okay, thank you very much. We have a lot of questions. Okay, the next one is from Joe Emmings. He has a lot of questions. Do you want to unmute? You just try to keep it simple because we have a lot of other questions. Please.
Yes, I'll keep it
Thank you.
simple. Thanks, Mike. It was a really great talk. So I have 3 questions. Okay. So one, what makes the Devonian special, or is it not special? But you know, if it is, this does indeed point towards a biological driver. 2, what is the interpreted proportion of sulfide derived from AMO, as in anaerobic methane oxidation, versus sulfate reduction? I think there's a very interesting aspect there in terms of thinking about why those carbonate concretions are sitting underneath your mineralized deposit, and maybe there's a lot of methane in the system. And 3, do you have any ideas about what the mechanism is for oxidation of lignin? You know, that's not very easy to do under anoxic conditions. But I guess I had one idea, is that it seems to me that if you've got a lot of labile organics in the system, you know, a lot of probably EPS and organic acids derived from biogenic silica, then maybe that's doing something called co-oxidation. So, you know, if you've got a lot of labile organics in the system, then that might be actually sort of promoting degradation of that woody material. So thanks.
Okay, so the Devonian, I think that, I mean, is it special? Like, I'm not entirely sure, but I think that the middle, it's possible, because in the middle Devonian we have all of these hebs forming here in Yukon, but also, and this is like, I didn't show this in the slideshow, but in northeastern BC, they're about the same age. And so if you look at then you look at the continental margin, I can go all the way back to the beginning here, just bear with me. Oh. And so in northeastern BC down here, we have some new data that we're still interpreting, but it suggests that it's about the same age, which would be a pretty compelling argument that, you know, then it's like maybe even a basin scale event, especially because there's lots of little hebs showings and properties and sniffs of metalliferous shales, even close to McMillan Pass and Howard's Pass and here in Selwyn Basin. And so it begins to look like if those are all the same age, and I haven't worked at any of the ones that aren't basically in Richardson Trough or associated with Acai, but if they're all the same age, then you're looking at a continental margin that's recording some kind of event in the middle Devonian that is in which highly metalliferous shales are being deposited, like at the scale of the continental margin. And interestingly, if you go to the Iphilian Gavidian type section in Morocco, there's also it's not nearly as enriched in metals, but you do see enrichments of platinum, nickel, palladium, and basically what is it's the type section. And so it could be some, and I don't know what the global scale event would be, other than that there are these biotic crises, massive global scale marine transgressions and black shale events that are depositing basically in the middle Devonian, like a global scale black shale event that could be helping to facilitate Hebs formation and maybe even the highly metalliferous ones in more specialized circumstances or places.
Yeah, interesting.
I think that that's, you know, that's like worth further research. Regarding AOM, so when I've been doing the organic geochemistry, we were trying to really fingerprint whether or not we could find those organisms that are responsible for AOM in the carbonate concretions and in the rocks around them. And so so far it's been a bust. But and I don't see why there wouldn't be AOM, because it has the characteristic signs. But usually with AOM, you see really positive sulfur isotope compositions as well. And we haven't really seen that in the Hebs proper. We've seen that in pyrite nodules around the head, like close to the Hebs, but not actually in the Hebs. And your last point, I would like to talk to you actually more about this maybe offline, because I don't know, I just know really about terrestrial organic matter being less labile, but all of the organic acids and organic acids associated with biogenic silica and stuff, I'm not terribly knowledgeable about.
Sure. Yeah, no, I'd be happy to talk to you. I mean, I'm probably not the expert in this either, but yeah, I'm definitely keen to talk to you offline about that. Yeah, it's really interesting. Thanks.
Well, Joe, thank you so much for all those questions. This is great. And I think just for the essence of time, we're just going to have one more question, and then we're going to switch to the second speaker. And I believe what we can do afterwards is we can actually separate the room. So if each of you want to stick around for more discussion, that's an option as well. So the last question that I'm going to ask is from a Mr. Plunkett, and if I can find his question for you.
Okay.
One moment, please. There it is. All right. Any ideas on how the concentrations of metals in the black shales is increased by so much relative to seawater?
So I think that in these deposits that there's very active particulate shuttling. And so I didn't show a plot that shows enrichment factor or molybdenum versus uranium, but it basically indicates that, you know, the relative particle reactivities of molybdenum and uranium and the much higher particle reactivity of molybdenum suggests that there's a very active shuttle of these ferromanganese oxyhydroxides, or at least iron-rich oxyhydroxides, shuttling metals down to the seafloor. And so in the modern ocean, these are super enriched, like the ferromanganese nodules and crusts have just a gargantuan amount of metals in them, like in the Clarion Clipper zone, or I mean, that's probably one of the best examples, but they form all over the seafloor, and they concentrate metals to a significant degree, and it's just basically time and being undisturbed. And so we don't have a great sense for how long these Hebs take to form. That's one of the things that we'd like to ultimately determine. But assuming that there's active particulate shuttling and a quiescent sedimentary environment, which we're pretty confident in, it could just be a matter of having the right amount of time and the right ingredients to do that.
All right, thank you.
There's a question for Mike from AB. I will read it. It's easier now, maybe. Okay. What is the average grade and thickness of the mineralization?
So there's not really like any grade or tonnage or anything like that, but it's usually weight percent level nickel, hundreds of ppb, platinum, palladium, usually tens of ppb gold, low thousands of ppm molybdenum, between low thousands to low weight percent levels of zinc, and tens of ppm for rhenium. And the average thickness is quite thin, realistically. I mean, the pictures that I showed are all pretty representative of what you could expect in the field. So 2 to 5 centimeters would be pretty average. And then occasionally you can run into thicknesses of approaching 10 centimeters, but that's pretty rare. And yeah, but there's no like proper resource estimates on any of these places.
Okay, thank you very much. We have another one. I think maybe it's the last one if no one wants more questions. So it's a question from Sean Johnson, but I think he is not here, but I will read it. In the exploration context, can you assign threshold values of high-enriched black shales or near high-enriched black shales versus background for regional explorers? And how do you see the comparison to the other large black shale deposits?
So I don't know the numbers off the top of my head, but there is a definition for hyper-enriched black shales, which is like, it's a sum of several elements, and it's above that threshold. It's like in the maybe 2000 ppm for a combination of zinc, moly, vanadium, and a few others. And so some combination of those elements above 2000 is the threshold for the hyper-enriched black shale. I mean, in terms of like in terms of the places that have produced this style of mineralization, I would say that they have probably higher thicknesses, like or the mineralization is thicker, like on the tens of centimeter to meter scale, perhaps, like in China, and that they're probably closer to infrastructure, or that they have a tonnage that's sufficient to really extract. But like this style of mineralization, especially in Yukon, is extremely remote. Like you're talking a minimum of like an hour or 45 minutes of a helicopter flight to get to one of these outcrops. And so there's no infrastructure, there's no roads, there's no anything. And so that's really that's a big hindrance in terms of, you know, getting out and exploring for them, but also even if there was like a really thick one, it would have to be very, very thick, or it would be tough to get. The lack of infrastructure is a real big hindrance to getting out there.
Okay, thank you very much. Wren?
Thanks. Yeah, I think we have time for one last question, and this is from Jerry B. It's another question for Mike. Jerry, would you like to ask your question yourself?
I can ask, can you hear me?
Yes, we can.
Okay, Mike, I was lucky enough to have been one of the geologists on the crew that, quote, found the Nick in 1981, along with Bruce Maurer and Ernie Olford. Did a little microprobe work, and Peter Lakuta identified vasite as the nickel-bearing sulfide species. And I did a little work that noted barium-enriched feldspars, possibly Celsian. I wondered if those observations have stood the test of time, and whether you have any comments on that or any other observations, particularly on the Celsian feldspar, because it's not a typical component in these SEDEX things in the Yukon.
Yeah, so definitely vasite. Vasite is the dominant nickel sulfide. There's a little bit of Gersdorfite, which is a nickel sulfosalt, sulfarsenide, but at the other places that I mentioned, it's millerite actually is the predominant nickel sulfide, and not vasite. And there's Celsian at all of the localities that I've seen and trace quantities. I did try to do some argon dating on it. Like I tried to get some Celsian separates out, but it was so fine grained that I couldn't isolate it to do any dating on it or anything. But it's definitely there. And it deserves to be worked on, probably, because it tells a part of the story about the history of the rocks. It's almost certainly a digenetic mineral, but I don't know much more about that.
Thank you.
All right, Jerry, thank you so much for your question. That is all the time that we have for today. Thank you everyone who asked a question, and we are sorry if we weren't able to get to your question. Mike and Bernadette are both available for any of your questions. And yeah, join us next week. Thank you everyone, and thank you to our speakers.
Yeah, thank you very much, and thanks everyone for coming out.
Thank you. See you next week. Thank you very much.